Okay, so we're going to do our chapter 2 section 2 doodle notes. So we're going to put our title, and our title is going to be Understanding Solutions. Okay. And we know that we have mixtures or solutions, and we learned about 3 major types. So we had our suspension, we had our solution, and we had our colloid. Okay. When we talked about suspension, we were looking at a solution that has large undissolved particles in it. Particles that can be easily seen and separated. Particles are seen. These notes are basically on the top half of your page. So particles are seen. And they easily settle or filter out. Okay, so then we talked about a solution. And a solution, good example of a solution is Kool-Aid. So we have our test tube, and we might have some grape Kool-Aid. Okay, so this is Kool-Aid. And what we learned about a solution is the particles are well mixed, so the color at the top is equal to the color at the bottom. And the particles are too small to see. And they are hard to separate. Okay, now we're going to branch a solution off into 2 parts, so I'm just going to put some arrows here, but we're going to finish this on the next slide, so just leave those arrows down at the bottom, and because that goes down to the second half of the page, and we'll finish that in a minute. So then we have our colloid, and our example of a colloid in our test tubes was a marshmallow. So we'll put our little marshmallow in here. Okay, and when we think about marshmallows, fog is a good example, Jello, mayonnaise, milk. They have small, undissolved particles. Okay, so they're large enough to see. They're not as small as a solution. They're large enough to see, but they still don't settle out. Notice our marshmallow is not floating in any water. We're just talking about the structure of the marshmallow. If we're talking about fog in particular, but also milk and jello, if you try and shine a beam of light through it, it won't go directly through because the particles scatter light. And even though the particles are large enough to see, they don't settle out. Okay, we're going to add more underneath here. We're actually going to draw a picture of fog, and then we're going to finish the rest of the solution. So we're going to keep going. Okay. Okay, so we're going to finish the actual solution part. So you see my two arrows coming off of solution. So we're going to finish that. We have two parts to a solution. We have a solvent and our solvent is our dissolver. Okay, and we know that the universal solvent is water. So we'll draw a picture of a universal solvent in here. Okay, and then we have the solute. Okay, which the U here, it's an arrow, reminds me of sugar. Right, and so in our Kool-Aid, we had little purple sugar particles. We will call Kool-Aid powder, and that was our solute. Okay. Now, one thing to remember is that when you combine water and Kool-Aid, you can no longer see the Kool-Aid particles. And that's because the water particles each have a Kool-Aid particle. Okay. So the particles can't be seen because they spread out and attach with water particles. Okay? So each little Kool-Aid particle is attaching to a water particle, and so they're no longer clustered together, so it's very hard to see the Kool-Aid powder. Okay, and then we're going to go under here, over here in this area, underneath the colloid where we wrote doesn't settle or won't settle. And I just thought it would be nice to write, to draw a picture of fog. So you've got your particles, and they're large enough to see, but they just kind of stay in the air. So if you're driving, trying to get my little bar going here, and you put on your lights, the beams are actually going to bounce off and scatter, and so it's very hard to see through the fog because a colloid will scatter light. And that's it for the front of the page. Now we're going to turn the page over, and we're going to talk about a saturated solution and how solutes affect boiling and freezing points. On the top half back of our page, so this is just going to be the top half of our page, we're just going to talk about really quickly what a saturated solution is. And the word itself means full. So if a solution is saturated, we would say that it's basically, we're saying that it's full. Okay, it's a full solution. And the best way that I picture this is if I have water molecules, so I'm drawing my little Mickey Mouse polar water molecules, and I were to put Kool-Aid in the solution. Because the sugary Kool-Aid is polar and the water is polar, they're going to attach to each other. And the best way I think of it is when every single sugar molecule is attached to a water molecule, when this happens, when every single one is attached, the solution is said to be saturated. Okay, so it's full. And if I were to add more sugar to this solution, there's no water left to dissolve it, and so it would just kind of settle to the bottom. So that's a saturated solution. Now we're going to go to the bottom half of your page, and we're going to talk about the effects of solutes. So on the bottom half, we're going to put the effects of solutes. Okay, and I'm just going to put my paper in half here. Draw 2 boxes. Now, when you add salt, so we are adding salt. When you add salt to like the road when it's freezing, when you're about to have ice on the roads, this is a C. I'm sorry, this didn't show very well. Okay, so when you add salt to a road, you are going to, the salt is going to get in the way of the water molecules, and so that's actually going to lower the freezing point of water. So adding salt lowers the freezing point. And how that happens is if you have water molecules and they're trying to form ice crystals, so they're trying to get together and make a crystalline structure, and you put salt in there, that prevents those bonds from forming into ice crystals, and so the salt gets in the way, and so the water has to actually get lower than 32 degrees in order to freeze. So it lowers the freezing point. So it has to be, if it's about to freeze outside, and let's say the temperature is going to get down to 31, 32 degrees, adding salt is going to prevent those water molecules from freezing, because it actually will have to be like a lower temperature than 32 in order for it to freeze. We also add salt when we're making pasta in our water, because adding salt will raise the boiling point. So adding salt raises the boiling point. So the same thing happens here, where you have the water molecules, and because they're attracted to the salt, because they're both polar, the salt will cling on to the water molecules. Okay, and so the salt particles will cling so much to the water molecules that the water molecules have a hard time evaporating, because when a water molecule evaporates, it leaves all the salt particles behind. It does not evaporate with the salt. And so the salt clings to water and won't let it evaporate. So now it has to get hotter than 212 degrees Fahrenheit or 100 degrees Celsius. And so that makes your pasta cook faster, because the water is trying to get hot enough to leave behind the salt particles and evaporate. And it has to get hotter than 212 degrees Fahrenheit because it can't let go of the salt particles. And that's all for those doodle notes.